Welcome friends. So we are discussing network theory. We are at module 7, which is mainly about transient response of series electrical network consisting of different elements like R, L, RC, RLC, etc. etc. Previously, we have studied the instantaneous behavior of inductor, capacitance, and using that conception we have studied the transient response of series RL circuit, then series RC circuit, and thereby we have studied series RLC circuit, and we have studied all of them by giving DC excitation. Now what will be the response if we give the sinusoidal excitation to a particular electrical network? So let us consider figure 10, a very important network. It's a very practical network. Figure 10, which is actually representing series RL circuit. Okay, now this series RL circuit, practically it roughly estimates or closely estimates a transmission line. What is transmission line? A transmission line is a line through which power is transmitted from the generation side to the load side. So a series RL circuit is closely resembles to a transmission line, of course under some specific conditions, and if that is given by a supply to a AC source, then that AC source you can consider this one as a generation side, or you can say it is a generator, and this generator is giving or feeding power to this transmission line via this switch. Now whenever switch is suddenly closed or open, whatever it may be, so for both of the condition this transiency will come in the network, and this side we have load, this side we have load side. Okay, so as far as the practical side is concerned, so this series RL circuit is very important. It closely reflects the practical side of electrical engineering. Now in order to study the sinusoidal or transient response of series RL circuit, now we shall continue our analysis. Let us say we have a voltage source that is equal to Em sin omega t plus theta. It is a well-known form of voltage source, sin omega t plus theta. Now this theta is called switching angle or characteristic angle. It is called characteristic angle. Now if we apply the KVL when the switch is closed, if you apply the KVL, then the straightforward equation is equal to the supply voltage equal to Em sin omega t plus theta, that is equal to Ri plus L di dt. Ri plus L di dt. It is quite straightforward. Now it is a new kind of a differential equation that has a sine term in it. So in order to solve this differential equation, we have the new form as the solution. So we have the new form of the solution, which is It plus Is, which is It plus Is. Now what is It? It represents the transient behavior of the electrical network. And Is the current response under steady state condition. So overall solution of this equation will tell you or will depict the entire situation including the transient state as well as steady state. Now let us evaluate one by one. So if we consider only IT, that is in order to evaluate the transient response of the current, then we must equate RIT plus LDIdt is equal to 0. Now this form, equation 23, is very well known. This form has been considered previously in case of a series RC circuit. You got this kind of equation, this kind of differential equation, and straight away you can write the solution of the equation is equal to IT is equal to K into e to the power minus T by tau. K into e to the power minus K into e to the power minus T by tau. What is tau? Tau is the time constant. Tau is the time constant, which is L by R for series RL circuit. So this is actually the transient solution of the series RL circuit. Now let us solve the IS, that is the steady state solution of the current. So in order to solve the steady state solution of the current, we write RIT plus LDIdt, that is equal to EM sin omega t plus theta, which is new. So from equation 25, the rest of the derivations are new. So RIT plus LDIdt, which is equal to EM sin omega t plus theta. Now the solution of this above equation can be written as I, that will be equal to A cos omega t plus theta plus B sin omega t plus theta. This is the common form of the solution. So if we take the derivative of this equation, so from this equation dIdt, you see the cosine derivative is minus sine, so it will be minus A omega sine omega t plus theta plus, now derivative of sine is cosine, so it will be B omega cosine omega t plus theta. So this is dIdt and this is I. So the dIdt is this equation and I is this equation, A cos omega t plus theta plus B sin omega t plus theta. So from equation 5, so this is equation not 5, sorry, it is 25. So from equation 5 you straight away substitute IT is equal to this and dIdt is equal to this into equation 25. So equation 25 becomes R into IT. So this is IT, A cos omega t plus theta plus B sin omega t plus theta. This is I, R into I, okay, plus L dIdt. So L into dIdt. So dIdt is this, you see, minus A omega sin omega t plus theta plus B omega cos omega t plus theta, and that should be equal to EM sin omega t plus theta. So essentially this is actually I, this is actually I, and this is actually dIdt. So now if you simplify, if you take cosine terms together, so you should get, with this cosine term you have a AR, so this is AR, and with this cosine term you have a omega BL, so it is omega BL or omega LB. So this is, so if you take cosine terms altogether, the coefficient of cosine term will be AR plus omega BL. Similarly, if you take sine terms together, then with this sine term we have first BR, so this is BR actually, and with this, from this dIdt term we have sine term with minus omega AL, minus omega AL. So we have BR minus omega AL. This is actually sine omega t plus theta, and with this actually cos omega t plus theta. So with this we have Em sine omega t plus theta. So if you compare this equation, so from equation 27, if you compare, at the right hand side there is no cosine term, so AR plus omega BL must be 0. AR plus omega BL or omega LB must be 0. From there you can evaluate A is equal to minus omega LB by R. This we can write. And if you compare the sine terms, then it must be BR minus omega AL, that must be equal to EM. So BR minus omega AL, that must be equal to EM. So from there, if you substitute A is equal to minus omega L B by R in this equation, actually this is actually A. This is actually A. Okay. So omega L into A, you substitute A is equal to this. So if you substitute or if you simplify further, so if you take B common, so this equation actually BR minus omega L into minus omega LB by R into EM equals to EM, sorry. So if you take R LCM, so B is common, so inside it will be R square plus omega square L square, that is equal to EM. So with that, so B is equal to R into EM by R square plus omega square L square. That is the value of B we have evaluated. So now from 28, having evaluated the value of B, so if you substitute this V value into this equation 28, so you will get A is equal to minus omega LB by R. So if you substitute minus omega L by R, so this is actually B, just we have evaluated, right? Just we have evaluated. So if you simplify, then A will be equal to minus omega L by R square plus omega square L square into EM. So we have derived two constants. A is equal to minus omega L by Z square EM, and B is equal to R by Z square EM. Now what is Z square? Z square is nothing but R square plus omega square L square. From the conception of AC circuit, series AC circuit, if R and L are connected in series, so they can be represented by an equivalent impedance which is equal to R square plus omega square L square. So from there we know Z square is equal to R square plus omega square L square. So from A, okay, so from A by Z square into EM. So with that, let us write the equation just like that. Minus omega L by Z, this is one term, and we have EM by Z, another term. And B we take R by Z, one term, and EM by Z, another term. In this way we are splitting. Now from the power triangle, if this is R and if this is omega L, and if this is z, this becomes phi. So omega L by z becomes actually sin phi. Omega L by z, that is become sin phi. So A is nothing but minus Em by z sin phi. A is nothing but minus Em by z sin phi. And similarly R by z, it is actually cos phi. R by z, that is equal to cos phi. So R by z, it is actually cos phi. So B is equal to Em by z cos phi. So we have the solution I is equal to A cos omega t plus theta plus B sin omega t plus theta. We have started from here. So we substitute A is equal to minus Em by z sin phi. So this is actually A into cos omega t plus theta, and we substitute B is equal to M by z cos phi. So this is actually the value of theta. So if you take M by z common, so altogether this equation is nothing but it is is or steady state behavior, that is Em by z sin omega t plus theta minus phi, which is is. So once you got this, so you can write the total equation or total solution including transient behavior and steady state behavior. We have the total solution I, that will be equal to k into e to the power minus t by tau plus Em by z sin omega t plus theta minus phi. So this is the entire current equation. So now if you plot this curve, you shall get a curve like this. So let us understand what is this. So from this point, before this point, the current was like this. It is sinusoidally varying current. Now at this point a sudden rise is there. So we can say that this is the inception of the disturbance or inception of the switching. Inception of the thing. So when this inception of the switching happens, so the sudden rise of the current happens. It is quite clearly observed that it is the sudden rise of the current. So actually this part or this region of this response is actually the transient nature. It actually representing the transient nature of this current waveform. Now if you move away from this inception of the switching, more you move, you can see this disturbance is decaying, it's starting decaying slowly, and ultimately it will settle down to a fixed value. So basically this envelope is determined by this transient factor or this factor IT. This factor IT, k into e to the power minus t by tau, this nature, and this sinusoidal response is actually determined by this factor, steady state response. So when you club them to get the total response, you should get this type of response. You have initially we have the disturbance is very dominant, so transient behavior or transient effects is so dominant. the more you go or more you move away from the inception of switching, so the effect, naturally the effect gets reduced and it will be dying, or it will be damping out quickly, and this entire time instant can be split into three parts. One is subtransient period, another one is transient period, and final one is a steady state period. Subtransient period is just after the switching, when the disturbance is so large. After 1 or half cycle time, when that phase gone, then somewhat it is the intermediate state between transient and steady state. So that is why this phase from here to here, maybe 2 to 3 more cycles, it is called transient period. And after this state, we have C state, which is called steady state period. And in this phase, observe that this response is clearly maintaining a steady sinusoidal response. And this type of waveform you can observe in case of a power system fault. In case of a power system fault. So whenever fault is very much transient phenomena, so whenever fault occurs in an electrical system with this network, this series RL network that is mostly resembles our electrical network, then we should get the current waveform in this fashion, in this way. Okay, so it has a subtransient period, transient period, and steady state period. So with this, I am ending this part of this lecture. So we shall continue this from the next session. Thank you.